Okay, we're back for some more of Ksp and solubility. And this time they want me to calculate the solubility of LaF3 in grams per liter in water, so not in molarity, but the problem is going to work the same way. So I'm going to first start out by writing my equation. Right, and I don't know what the solubility is. This is going to be x, x, and 3x. And then I'm going to write my Ksp expression. It's going to be La times F minus, and this is cubed. And La is going to be x, and F is 3x, and this is cubed. And I can look up my Ksp for LaF3, and it's 2 times 10 to the minus 19th, and 3 cubed is 27. Then I'd have x cubed times another x would be x to the 4th. So I'm going to take 2 to the negative 19th divided by 27, and then to the 1 divided by 4 power. And I got 9.3 times 10 to the minus 6th. And this is molarity, which is moles per liter. So if they want me to find it in grams per liter, 1 mole is so many grams, which is the molar mass. So I'm going to find the molar mass of LaF3. And that molar mass is 195.9. So multiply that times the 9.3. And I got 1.8 times 10 to the minus 3rd grams per liter. Okay, so not a whole lot different than what we did before, except this time we found it in grams per liter. Okay, now the next one wants me to find the solubility if I'm adding Kf to it. So I'm adding a common ion. And we know from our discussion of adding a common ion when we talked about buffers, that if we add a common ion, it reduces the solubility. So we'll go ahead and we have the same equation. LaF3 makes La and 3F minus. And we had x and 3x. And now we're going to add to this 0.10 of my F, because we know this is going to split apart completely. So if it was 0.1 Kf, it's 0.1 of K and 0.1 of F. So I'm going to have x, and 3x plus 0.1. And I don't take that times 3 because this is all I got from the Kf. So we still have our same Ksp, 2.0 times 10 to the minus 19th. And this is going to be equal to x times, it's now 3x plus 0.10 cubed. Okay, and we're going to say that this solubility of x is very, very small because we're dealing with slightly soluble salts. So since it's very small, we're going to cross this out, just like we did last time, and assume that that's going to be very small. So I'm going to take 2 to the minus 19th divided by 0.1 cubed to find x. And that's moles over liters. And they still want me to find grams. So I'm going to use the same molar mass I had last time because it's the same thing. 195.904 grams. And now I got my solubility to be 3.9 times 10 to the minus 14th grams per liter. And before it was 1.8 times 10 to the minus 3. So this is much, much smaller. Okay, then we have one more problem. And this one wants me to find the solubility of MnOH2 in grams per liter when it's buffered at a pH of 9.5. So the first thing I'm going to do is I'm going to find my H plus from my pH. So 10 to the negative 9.5. Okay, so that's my H plus. And then I'm going to write my equation for MnOH2. This is Mn plus 2OH minus. This is X, this is X, this is 2X. And then I am adding, this is my H plus. I'm going to need to find my OH minus. So I'll take 1 to the negative 14th divided by that 3.16. Okay, and I got 3.16 times 10 to the negative 5th. Okay, and my Ksp expression is going to be my Mn times my OH minus squared. And they gave me my Ksp, and it's 1.6 times 10 to the negative 13th. I looked that up in my book. And then my Mn is X. And my OH is 2x plus 3.16 times 10 to the negative 5th squared. And once again, we're going to assume x is very small. So we'll get rid of that. So 1.6 times 10 to the negative 13th divided by 3.16 to the negative 5th squared. And I got x is equal to 1.6 times 10 to the negative 4th molar, which is moles per liter. And then since I want it in grams per liter, I'll have to find the molar mass. And then I'll add that, let's see. Got a molar mass of 88.95 grams. And for my solubility, I got 1.4 times 10 to the minus second grams per liter. And that should conclude the second lecture.